Okay guys, so we can start now. Pardon for the delay, I was in a meeting with my professor. Okay, now we can start. So currently we are in the week 12 and we went through the concepts that has been taught in this particular week, and they are as follow. The topic covers are true stress, true strain. Then we cover about the creep, effect of the stress and temperature on the creep. So in like these three sections we have covered the creep. We discuss what is creep, under what condition this particular will work, and also what are the factors that is going to affect this particular creep. For example, temperature we saw, and we saw the stress, how they are going to affect the strain rate. Okay, then we discussed about the list of the mechanism that is going to affect the creep mechanism. Okay, and then next three part we discuss about the composite, and we saw the behavior of the composite in the isostrain and the isostress condition. More or less, in gate exams in every year, one question among this particular isostress or isostrain will come. We are also going to solve a couple of questions based on that. Then later on we discuss about the fracture, and then ductile to brittle fracture. Fracture, for example, we discussed that there are the two types of fracture. One elastic and one is the plastic. Sorry, one is a brittle fracture and one is a plastics. Okay. So in how they are differing from each other? They differ from each other in a way that the energy absorbed. Okay. So in the case of plastic deformation, we saw that the energy absorbed will be more. While if we see about the brittle fracture, energy absorbed will be very less. So these are the list of the things that we have covered. And one of the most important part regarding the Griffith criteria. We saw the role of the crack. We saw how it is going to affect the Griffith criteria. For example, the stress required to fracture a crack of particular length, let's say C, it is 2 gamma E divided by pi times C, where C is the crack length. Here we saw that if we keep on increasing the crack length present in the specimen, you will require less force. Increase the C, the sigma required will be lower. Right. So in this case, we will get the low stress. So it means that the material is weak, right? So these are the list of the things that we have covered, and for example, at the end we discuss about the ductile brittle transition temperature, how we can strengthen the particular glass. For example, toughening mechanism we have saw, ion exchange we saw that, and then we very little we not went in too much advanced way for this fatigue failure. We discussed just about the introduction of the fatigue, that is a cyclic loading. Okay. So these two are the list of the topics that we have covered in this particular week. Please let me know if there is any confusion till now in this week, any concept that you want to rewind. I have a doubt in the diffusion mechanism of the creep. Okay, yeah, please. Please let me know what is the confusion, then we can clear it out. Let me check I think I have already took, I also wanted to discuss that particular part. Yeah, here it is. In the last year also I took this particular course as a TA, and there also we found that the diffusion part in the creep it's little tricky. So what is happening over here? We took a grain, we took a one particle, let's say. You can call it to be the grain also. Now, for that particular grain, what we are doing two things. First, we took it to the high temperature T. Second, we are applying the stress. Okay, so for example, what will happen? Let's say you have a plastic material. What you are doing, you are applying the load to it. Let me see if I have any rubber band with me. Okay, not here. What will happen, like if I have a rubber band with me and I'm trying to apply some force, what will happen? It will elongate in the direction in which you have applied the force. In that particular direction, my rubber band is going to elongate. Similar type of things are going to happen here also. We have applied the force in this. So at the end, what will happen? Our result will be like this. It will be something like this. Right? But the thing is that how it happened? It happened due to the diffusion. Here, let's say these are the atoms initially. Now under the application of the force and the temperature is required in a way that you have to create the vacancy for the diffusion to migrate. We have saw in the class, I think in the week 6 or week 7, that if you go to the high temperature, the vacancies will be more and more, and that's the reason like our vacancy migration can happen. An atom can migrate. Okay, so when we went to the high temperature, the diffusivity we have increased. Now giving the stress, we are allowing the system to undergo the elongation in one of the direction. So what will happen? This particular atom, they will diffuse to this side of the grain. So the atom which were perpendicular, which were parallel to the stress axis, they will move and they will go to the region which is perpendicular to the stress axis. This is my stress axis, and this is perpendicular. So from this atom is going from this particular region over here. Okay, like this. Why specific to the perpendicular direction? See, we are not very specific for the perpendicular. What I'm telling is that it will go along this particular direction in which the stress is applied. So the thing is that it will go along the stress. For example, here also, when we try to elongate it, when we applied the stress, what happened? It flow along this particular thing. Right? So now what we are applying the force over here. Okay, so this planes of atom will try to diffuse to this particular direction, and it will go to the region where the things were empty. Okay, where the vacancies was more. Okay, so now see, by the application of force, by the application of this stress, what we are doing, we are creating the vacancy gradient. So we can, by application of the force, by application of this particular force, we are creating a vacancy gradient. Here the stresses along this particular direction is there. Like for example, I have let's say I'm talking about the single crystals, and I'm applying the force over here. What will happen? The plane will expand, right? While this particular type of plane, they will try to contract. Like in this direction, it will contract. In this direction, it will expand. So by application of the stress, we are creating the vacancy gradient, and this vacancy gradient is there in between this perpendicular and the parallel planes. Now whenever the gradients will be there, a diffusion will happen. We have saw in the class of the diffusion that whenever we are creating the gradient of here the atom was there, here the atom was not there, let's say. Okay, we are trying to expand this particular grain boundary, it will go. So what will happen? atoms are moving in this particular direction, but the vacancy will move in this direction. And this is the reason that why our initial, which was something like this, it will elongate along one of the direction and it will go something like this. This is the reason why we are calling diffusion creep as a stress assisted diffusion. This application of the stress is causing the diffusion to occur. Okay, so the gradient is there in the stress. A gradient one can create in multiple ways. For example, the temperature. Let's say I have this is my material. Here the temperature, this particular plane, this page is my material. Let's say here the temperature is high and here the temperature is low. What will happen? Here the diffusion will be faster, here the diffusion will be slower. So in a way, whether we are applying the temperature, whether we are applying the electric field, or you pass the current through your specimen, or you apply the stress, what they are doing, they are creating some gradient across each other. And this gradient, here we are saying it is about the vacancy. And then they will try to diffuse. We are not going into the advance of this. Obviously, there are the equations. Is it like the atom hop through the vacancy and settle at the grain boundary along the direction of the stress? Yeah, it is like that. It is that only. So the application of the stress is causing this gradient to occur, and that is what leading to the diffusion. Okay. Also, this is vacancy assisted. So here we say that vacancy migrate from the grain boundary, which are perpendicular to the stress axis, to the grain boundary, which are parallel to the stress axis. So what I talked about is the atom. What professor has noted down here is from the perspective of the vacancy. Obviously, if the atom is moving in this direction, then the vacancy is moving in the opposite direction, right? So this is about the diffusion creep. Again, we will come back to this particular figure, because I have question number 6. I have one question which is related to match the following in the creep based on the mechanism of the creep. Let me know if there is any doubt in this. Okay, great. So Omkar and Gitu, if there is any other additional questions are there, please let me know, so that before I go to the problem solving, we can discuss the concept which are not clear. Okay, great. Since there is no doubt, let's go to the question number 1. True and false. True stress is always greater than the engineering stress in tension. The condition is given. So the question is saying that true stress is greater than the engineering stress. Is it true? Okay, it's true. Very good. Now let's see why it is. It's true. That is good. So now what we have is that let's say this is the engineering stress 1 plus epsilon, and this is a true stress. This equation we have saw in the class that true stress is equal to the engineering stress times 1 plus epsilon. That is strain. Okay. And in the case of tension, when we are talking about the tension, which is specified over here, the strain will always be greater than 1. Sorry, it will always be positive, not greater than. Strain will always be positive. Since this is a positive quantity, it is going to add over here, and so sigma times of this, like the true strain, will be greater than the engineering strain. Okay, so with that we have solved the first part of this. If any doubt in this, let me know. If not, let's go to the next part. Volume constancy is a valid assumption for both elastic and plastic deformation. True and false. So Omkar and Gitu, we can see that in the elastic what happened. Whenever we are applying the elastic, so for example, this is my planes, I am applying the force, what will happen? The plane will expand. So the volume constancy is not valid in the case of elastic. It is only valid for the plastic. Okay, this is false. In plastic deformation, the volume is not going to change. In the elastic deformation, the volume is going to change. So the volume constancy, this assumption is only valid for the plastic deformation. Okay, so this is false. Any doubt? Let me know. The last one. True strain provide a cumulative measure of deformation regardless of the path reversal. True strain provide a cumulative measure of the deformation regardless of the path reversal. Is it true or is it false? In a class, we calculated, we went from the length L, we made it 2L. And again after we compress it back and we made it L again. So when we talk about the true strain, engineering strain, and here I am writing about the true strain. Engineering strain will tell us that change in the length divided by original. Initially there is 0. Here the change is what? Change in the length divided by original length. Change in the length, that is 2 times 2L, the final one, minus initial, which is L divided by L, initial L. So here we'll get L. That is like we'll get here 1, right? Sorry, not L, we'll get 1. Now again, now come back here. Now here we are compressing back. Again the change in the length divided by original length. Here the change is, the final is L and initial is 2L. For this particular case, the initial will be this one. And then we will divide it by the initial n, which is 2 times of L. What we'll get here is minus of 0.5. Add them up. What you will get? You will get that here 1, 0, 1, 0.5. Here it will say that the 0.5 of strain is there in the sample. But we can see my initial and the final, there is no strain. They are exactly same. Let's talk about the true. True strain, we know that it's a ln of L over L naught. Initially L over L naught, L and L naught, they are exactly same. So there is no change. So here the ln of 1 will be 0. What about here? Ln of L, that is 2L divided by L naught, which is L. Here will be ln of 2. Now here in this case, when we are going from this particular to this particular place, here it will be ln of L, which is final is L, initial is 2 times of L, right? So here we will get minus of ln 2. Add them up. Addition will be 0 plus ln of 2 minus ln of 2, which is equals to 0, right? So true strain, when we add all of them, what we'll get is the cumulative value. So true strain provide a cumulative measure of deformation regardless of the path reversal. See, we reverse the path. We went from this to this, and then we went from this to this. So regardless of the path reversal, we'll get the true value, which engineering strain is not giving us. Okay, so this is a true. If instead of true strain I write engineering strain, then the answer will become false, right? So the final answer is true, false, and true. Okay guys, this is the question number 1. Let me know if there is any doubt in this particular question. Clear? Great, Omkar. Perfect. Let's move to the next question, question number 2. In the demo, which we saw in the, when we are talking about the creep, we saw in the class that the Srikant, the assistant to the Professor Rajesh Prasad, he demonstrated that something. He demonstrated the spring, two spring, and there we saw that spring 2 was undergoing the elongation with time. Spring 1 was remaining as it is. It was the professor who stretched it further and made it to undergo the plastic deformation. But when we talk about this particular spring 2, it doesn't need any additional stress to deform. So with respect to the time, the second spring was keep on deforming. Here is a strain. Okay, let's see the question. In the demo, the lead tin solder melting point is given to us. Spring crept at the room temperature because, now what is the reason? A, B, C and D. Why it creep at the room temperature? Option A, very good Omkar. The option A is the right answer over here. What is the requirement for any material to creep? The test temperature, the temperature at which that particular test is going on. For example, right now our test temperature is room temperature, divided by the melting point of that particular material. Both of them should be in the Kelvin, and it should be more than the 0.5. Sorry. Right. So what we have to do over here, if I want to find at what temperature my specimen is going to creep, what is the minimum temperature I should provide? So it will be T will be greater than 0.5 times of Tm. So if it is more than this, if the test temperature is more than this, then my material will undergo the creep and this particular deformation will take place. Now for our case, 183, the test temperature is 183 degrees Celsius, capital T. But we have to convert it to Kelvin, right? So what we'll do, we'll add 273 divided by the, the test temperature is room temperature. So 25 degrees Celsius plus 273 divided by the melting point 183 plus of 273. This is just to convert to the Kelvin. Okay, we can easily do, and you will find that the value is 0.66, which is more than 0.5. This value is more than 0.5. So this temperature, the room temperature is sufficient enough for this particular lead tin solder to undergo the creep. So whenever we have to take a lab for the VTech, we have already purchased this particular lead tin solder wire, and what we do, we have wire, we not have the spring. So what we do, we just apply the little bit of load, which is obviously lower than the yield point, and then we tell the student, okay, you take the reading after an interval of 5 minutes, 10 minutes, and then 1 hour and 2 hour, and then plot this particular curve with respect to the time, how much stress you are getting, how much strain you are getting. Okay, so with that we have solved this question number 2. Let's move ahead. Let's go to the next question, question number 3. The question is, with the melting point given in the brackets, take those material which will creep significantly at temperature of 180 degrees Celsius. Right. Our condition is still the same. The T over Tm, if it is greater than 0.5, then the specimen will undergo the creep. Right. What is given to us is the test temperature 180 degrees Celsius. We'll write that 180 degrees Celsius plus of 273 divided by melting point, it should be greater than 0.5. We can rearrange the term. What we'll get, 180 plus 273 divided by 0.5 Tm. Gitu is saying the answer is A. Okay. What about Omkar? See, we can do it easily. Where is my calc? Okay, so let's try to find 180 plus 273 divided by 0.5. 906. But again, this is in the Kelvin. What the value has been given 0.755 for the option A. Very good. So 0. Okay. So okay, you are doing one by one for each of them. My aim is to find that directly what is the range for this TM. We can go in the both the way. That is right. Let me tell you, there can be more than one answer correct. So now what we got, the melting point should be less than 906 Kelvin. Right? So let's convert it to the degree Celsius because the values given to us is in the degree Celsius. So what we'll do, 906 minus of 273. Okay. Okay, so only one answer is the right answer over here. I changed the value maybe. Okay, so only the lead will undergo the creep. I was supposed to make it little bit more this temperature so that we can incorporate aluminum also, but I think I messed up with the, while making the question I messed up with the options. Okay, so what we have got over here, only the lead is the one which can undergo the creep. Which are the material which will not undergo the creep? They are this. Clear? Okay, great. Let's go to the next question, question number 3. Sorry, question number 4. If the melting point of the polyethylene is this, it will not creep at which of the temperature it will not creep? Again, we'll apply the same. Okay, option D. So Gitu has told that option D, it is not going to creep at this particular temperature. Right? Very good. That's the right answer. Let's just do calculation over here. So T over melting point is given to us 140. So 140 plus 273, 0.5. Okay. So we can find the value of T. T should be greater than 206.5. This is in the again Kelvin. Then what we can do is minus of 273. So we'll get T should be greater than minus of 66.5. Okay, so only this value is lower than that. Remaining all the values, room temperature 0 degree Celsius and minus of 60 degree, they will show the creep. Only this particular temperature we will not get no creep. Okay. With that we have solved this question number 4. Any doubt, let me know. If not, let's move to the next part, question number 5. No sir. Okay, great. Yeah. So the question says that for a given material, doubling the applied stress at constant temperature will halve the steady state creep rate, double the creep life, increase the creep rate. So mostly it is on the creep rate. We know that we saw in the class there is a formula. Creep rate will depend upon this. So we know that, let's say, since we are only talking about the applied stress, so remaining all the factors are constant, so T is constant. So here we can see that the stress, the creep rate is directly proportional to the stress applied to the power of n, and n is the stress exponent. What will happen? Doubling the applied stress. Okay, let's say the the first one was this initial strain, which is corresponding to the sigma to the power of n. The second one, now we doubled the stress, right? Instead of sigma, now it is 2 times of sigma. Now what is going to happen to the strain rate? We can find from here. We can divide initial divided by final. It will be equal to the sigma to the power of n divided by 2 times of sigma the whole to the power of n again. So from here we can find that the sigma final will be equal to the 2 to the power of n times sigma, sorry, strain final will be equal to 2 to the power n times strain rate initial. So what happened? The strain rate got increased. If you increase the load, the strain rate will also increase. This is what we have saw in the class. I increase the stress. Okay, let's go. It was going like this. Now, initially it was like this. Now I increased it. So what will happen? It will go like this. Initial value will also increase. I should make it more stiffer compared to this. So this slope and this slope is double of like 2 to the power of n times. Okay. So with that what we can say that it will increase the creep rate by the factor of 2 to the power of n, which is this factor. So option C is the right answer over here. Right. So all we are supposed to know here is that the strain rate in the creep is depending upon the two terms. One is the applied stress, and second is the temperature at which the creep has been carried out. Creep experiment has been carried out. In a GATE exam, I saw that, and a couple of interviews also. There, people consider, they ask more question on this part. They change the temperature and tell that, okay, now calculate what will be the strain rate. Okay, so simple only. It will involve more of the mathematics. When we talk about the stress, it is very straightforward that the factor by which we are increasing the stress, then the same factor to the power of exponent, our strain rate is going to increase. Okay. So with that, you have solved the question number 5. Any doubt, let me know. If not, let's go to the next part, question number 6. Here, it is regarding the creep mechanism. The first one, cross slip. Which one will be the right answer over here? For the cross slip, we know that cross slip happened. Very good, Omkar. Option B. Cross slip happen in the case of screw dislocation, and it is nothing but a screw dislocation changing the slip plane. What about the climb? Option C. Very good. So it is a edge dislocation moment perpendicular to the slip plane. It was like this, like we had the plane, and here is the obstacle. Our edge dislocation came here, and now what will happen that it found this obstacle, and now it will move perpendicular to it. And it will try to bulge. Okay, it will go like this. Diffusion creep. We discussed today. Yeah, very good. Option D, however, stress assisted atomic migration. Okay. The last one, grain boundary sliding, is a grain boundary movement at the high temperature. Option A. Okay, just let me write the answer. 1, 2, 3, 4. Here the answer is B, C, D, and A. With that, we will solve the question number 6. Let's go to the next question, question number 7. Okay, let's do it one by one. True and false. Creep deformation can occur at constant stress. Very easy. Creep deformation can occur at constant stress. True. Very good. Diffusion creep require dislocation motion. So what we have saw, yeah, very good. What we have saw that diffusion creep, it's the migration of the vacancies from one of the particular plane to the another. Okay, let's go to the next one. Grain boundary sliding is more prominent at low temperature. Grain boundary sliding is more prominent at low temperature. For for grain boundary to move, it will require more temperature or the less temperature. Obviously, it will require more temperature. At the high temperature only, the diffusion will be faster. Okay, very good. It's a false. Let's go to the next part, the last one. In in climb, vacancy assists in the movement of the edge dislocation. Uh, Actually, the answer is true here. For example, let's say I have a edge dislocation. Above, just below it, there is no plane. Here there is no atoms, right? Now, for example, let's say this is nothing but a dislocation. It is not only like this. Like if I go behind, also there is a array of atoms are there. So my dislocation is also there. Okay, so if I see from this direction, it will be like this. If my dislocation want to move from this and it want to climb up, it want to go in the up direction, what it should do? It should lose this atom. This atom, it should go to the one of the vacant site. Okay, let's say this is a vacant site for, okay, so it will go over here. So what will happen? Now the dislocation which was over here, now this atom also left. So what will happen? The dislocation will move up. If this atom also will left, the area of atom, now again dislocation will move up. This is the dislocation climb, right? So for the edge dislocation climb, the vacancy is assist in the movement. Okay. So here this one is true. So the final answer is true, false, false, and true. If any doubt in this, please let me know. We can have a discussion on that. If not, let's go to the next question, question number 8. For glass fiber reinforced plastic, composite with, see, EM, EF, see, M, we know that it's a matrix. This is the modulus, Young modulus of the matrix. Here, it's a fiber. F is a fiber. What is the EC? EC means the clear, but last question once more, sir. Okay. Question says, in climb, vacancy assist in the movement of the edge dislocation. Let's have a discussion on this. this vacant site I left it. This site I purposefully I left. These are the vacant site. These are the vacancy. Now we can see this is my dislocation. If dislocation want to climb, what it should do, this is my initial case, and this, let's say this second case is the one which I want to happen. So initially my dislocation was along this particular plane. Now here we can see my dislocation has moved and it came to this. So what happened? The dislocations climbed. This is dislocation climb. Now for dislocation to climb, see what is this? This is the array of atoms. This is one atom. Behind that will be the more atoms. Okay, because dislocation is a line defect. Just this is the atom. Now what from here, from the case 1 to the case 2, here the atom was there initially, now it's not there. So what if dislocation want to climb up, it should lose this particular atoms, the array of atom. How it can happen? This can go to this vacant site. If this go to this vacant site, and this has been occupied now by the atom which was over here, so the vacancy has assisted the dislocation climb to happen, right? So this dislocation climb was assisted by the vacancy. If there are the vacancies present, then dislocation climb can happen easily. Also, this will require the high temperature. So my initial dislocation, which was over here, it has climbed to over here. In order for this to happen, this to do dislocation to climb, it should lose these particular atoms, the array of atoms. If these atoms are going where they should go to the vacant site. Okay, so this is what has happened. So now let's see the question. In climb, vacancy assist in the moment, which is true, of the edge dislocation, right? So we did the climb, and the vacancy was the one which is assisting this particular thing to happen. If you have less vacancy, let's say if you don't have much vacancy, so in that case your dislocation climb will be very difficult. Okay, less vacancy will restrict dislocation climb, will retard dislocation climb. One thing we know, if I increase the temperature, my vacancy concentration will also increase, and so my dislocation climb can happen. So this is the reason why dislocation climb happen at high temperature. Okay, is it clear now, Omkar and Gitu?
Yes, sir.
Okay, great. Okay, so we have completed this question number 7. Now let's get to the question number 8. The question says, so we were discussing M is a matrix, F is a fiber, C here mentioned is a composite. So composite is made up of the matrix and fiber. Now the question is given, it is mentioned that we are in the isostrain condition and we have to find the modulus of the composite. We know the modulus of the matrix, we know the modulus of the fiber. Also we know by what volume fraction we have added them. Their addition of volume fraction is 0.5. Okay. So we have discussed this in the class that modulus of the composite will be given by the modulus of the matrix times fraction of the matrix plus modulus of the fiber times fraction of the fiber. Okay. Now here we know that whatever the f value is given, it is a fraction of fiber. Very important, people usually get forget that this fraction of fiber is a volume fraction. Few questions just to confuse you, they will give you in the weight fraction and they will also give you the molecular weight also, so that you can convert, or density. Okay, like you can make a conversion, but they will mention in a way that you will directly feel like you will use that particular weight fraction, which is not the case. Our question required the volume fraction. This particular equation is valid for the isostrain condition. Now we can apply our formula. Fraction of the fiber is f, so fraction of the matrix will be 1 minus f plus modulus this times f. Now we can substitute the values. We know all the values from here. Modulus of the matrix is 2 GPa, 1 minus f is 0.5 plus modulus of the fiber is 70, and again the fraction is 0.5. Okay, we can easily do this. This is 0.5 and this is also 0.5. So what we'll get, 1 plus 35, which is 36. The unit is GPa, here is also GPa, so the final answer is in the GPa. So here we can see that the matrix which has low Young modulus, 2 GPa, we have converted by adding the fiber into that to the 36 GPa, right? So with that our answer is option A. Clear, guys? Okay, let's go to the next question if there is no doubt. Question number 9. Note that we discussed the isostrain condition. One more way people usually represent the isostrain condition, question says about the isostrain condition without mentioning the word isostrain. They will use the word longitudinal direction. Okay, if this word has been mentioned in your question, so it means that the isostrain condition is there. If it is transverse, then it is the isostress. Okay, we know they both are differ from each other. Let's do this true and false question. The first one, the isostrain model predict higher modulus than the isostress model for the same f. Okay, isostrain model predict the higher modulus than the isostress modulus for the same fraction. Is it true or false? It's true. Very good, Omkar. From here, if we start and go here, let's say this was the matrix and this is the fiber, and so this will be the isostrain. Again, the modulus is over here, and this will be the isostress. So isostrain predict higher modulus. Always it will be higher than the isostress. Isostrain will be higher than the isostress for a given fraction. Okay, for a particular fraction we are talking about. Also, isostrain is the upper bond we have learned in the class, and isostress is a lower bond for any uh, matrix, any composite. Okay, let's go to the next part. Question number B. The isostress condition require the matrix and the reinforcement to have identical Young modulus. This is the requirement? It can be the same, it cannot be the same. This is not the requirement for the isostress condition. Okay, so this is false. Let's go to the next part, question number C part C. In the isostrain model, EC increase linearly with the fiber volume fraction. Is it true? The composite modulus will increase linearly with the fiber volume fraction. So here we saw that it is true. Very good. Okay, we saw that E of the composite will be equal to the modulus of the matrix times 1 minus fraction of the matrix plus modulus of the fiber times the fraction of the fiber. Okay, so here we can say that, for example, this will be constant. The only variable here is the f. I can rearrange this particular term. I can write em plus f times ef minus em. See, this is constant, this is constant. So EC is varying linearly with f. If f will increase, this will also increase. So this is what we have saw. They are following the linear trend. Okay, very good. The last one. The isostress modulus equation is derived assuming equal strain in all the phases. Isostress require equal strain in all the phases. True or false? It's a false. Very good. What it required? It required the equal stresses because isostress. Okay. So with that, we have solved this question number 9. Let me write the final answer. True, false, true, and false. If any doubt, let me know. If not, let's go to the next question, question number 10. Okay, great. A continuous and aligned glass fiber reinforced composite consists of 40 volume percent glass fiber having a modulus of elasticity 69 and 60 volume percent polyester resin that when hardened display the modulus of 3.4 GPa. Okay, so it has this particular modulus. Okay, so it has the fiber and it has the matrix. Fiber is 40%, 40 volume percent, it's between 0.4. Here this is 0.6. Their modulus is given to us in GPa 69 and 60. Sorry, 69 and the 3.4. Compute the modulus of elasticity for this composite in the longitudinal direction. This is something which we have discussed. Longitudinal direction means what it implies, either isostress or isostrain. We discussed in the last question this part. This longitudinal direction, is it isostress or is it isostrain? Isostrain, right? Very good. So I have mentioned that. See few things now. This few things. Once you solve a lot of questions, then only we'll get to know that okay, these are the nomenclature they can use to confuse us. Instead of directly writing isostrain, they will use the word like longitudinal direction. We have to understand that this is the isostrain condition, not the isostress condition. We have to find the elasticity of this composite. Okay, we have to find this EC. Since we know which condition we are, we will apply that particular formula. Matrix 1 minus fraction plus modulus of the fiber times fraction. Okay, so this is we can find now. For the matrix, we know it's a 3.4 multiplied by 0.6 is a fraction, and here it is 69 and fraction is 0.4. Okay. I think I can leave it over here. It's very easy calculation one can do. Right. So with that, we have solved this question number 10. Okay, but just for the completeness, let me just write it down. So it is given as 29.64. Also note down that this value of 29.64, it is in between the values. Okay, so it is less than the fiber, it is more than the matrix. It will always be in between. Max to max, it can take this value, and minimum to minimum, it can take this value in the isostrain condition. That too corresponding to the 100% of the fiber and 100% of the matrix, which is no longer the composite anymore. Okay, so for the composite, the value will always be in between them. With that, we have solved the question number 10. Let's go to the next question, question number 11. Which type of fracture absorb more energy before failure? Brittle fracture, ductile fracture, both will absorb equal energy. Neither of them absorb any energy. Which one is the right answer over here? The question says which one is going to absorb more energy when we talk about the failure. Yeah, very good, Omkar. The option B, the ductile failure, is the one. We saw when we are talking about the ductile failure, our stress strain curve will go like this. While when we talk about this is ductile, and we talk about the brittle failure, the stress strain curve will go like this. So this is the energy that has been absorbed over here. And here the absorbed energy is this much. Right. So option B is the right answer over here. Very good. Let's go to the next question, question number 12. How did stiffer paper behave compared to the floppy paper with the same crack size? So this is the demonstration which was given by the Professor Rajesh Prasad in this particular week 12 video. So if I have a stiffer paper, how differently it will behave compared with the floppy paper? It tone more easily, stiffer paper easily. Okay, option B, it required more force to tear, right? Very good, Omkar. Option B is the right answer. So stiffer the paper, more is the force you have to apply to tear it, right? It's simple experiment, observation. Let's go to the next question, question number 30. A sample of glass has a crack of half length 2 micrometer. The Young modulus of the glass is given to us, and the specific surface energy is 1 joule per meter square. Calculate its fracture strength and compare it with its Young modulus. Okay, so our aim is to calculate the fracture strength. Very important thing, we are talking about the glass. Glass, we know it is a brittle. And when we are talking about the brittle material, Griffith criteria comes into play. If instead of glass, the question was talking about the metal, let's say it mentioned the copper, the Griffith criteria will not be into any play until unless they specify that that particular material or metal it's a brittle. Okay, they mention the material glass just for the sake that it is a for us to know that it's a brittle material and Griffith criteria can be applied to it. Our aim is to find the fracture strength sigma, which is equals to the root over 2 gamma e divided by pi times c, which is crack length. Now let's see the list of the information that is given to us. The crack of half length is given to us. So crack length, we saw in the class that crack length is given as 2 times of c or 2 times of a, anything you can call. What is given to us is a crack of half length. So let's divide it by 2. The crack of half length will be nothing but it is c and it is 2. So the value of c directly given to us, it's a 2 micrometer. Okay. The Young modulus of the glass is given to us, that is E. E is equals to the 70 giganewton per meter square. And the specific surface energy, that is gamma, is given to us, it's 1 joule per meter square. These are the list of the things that is given to us. Always, I find this always more comfortable to convert all the values in the Newton per meter square. So let's try to solve this question. 2 multiplied by gamma. Gamma is 1 joule per meter square, right? Multiplied by the Young modulus. 70. G is here, means 10 to the power of 9. Again converted to the Newton per meter square. Divide by pi multiplied by c. C value is 2 micrometer. I will convert it to the SI unit. 2 multiplied by 10 to the power of minus of 6. Okay. All the values are in the SI unit, Newton per meter square. What will be the unit of the stress which we will get? The value will be in the Newton per meter square. Can we easily solve this? Let's try to do that. What we'll get is root over. Let's simplify. 1 0 is here. 9 overall 10 to the power of 10 minus of 16. It will again add 10 to the power of 16. Okay. 7 by 2. We can cancel this. 70 we have consumed, like 0 we have consumed. So what we are left with, 7 divided by pi. So what we got, root over 7 by pi 10 to the power of 8. Let's calculate this value. Root over 7 the value which we have got is 1.49 into 10 to the power of 8 in the Newton per meter square. Let me write in the mega Newton per meter square. I can get 10 to the power of 6, 149 mega Newton per meter square. So this is the stress required. This much, 149 the stress will be required for the fracture to happen. Compare it. So our first task is done. Compare it with the Young modulus. Young modulus is what? 70 G is given, right? So 10 to the power of 9, 70 into 10 to the power of 9. What this is? It is 10 to the power of 6. Okay, 149. Approximately, if you divide roughly, it is 2 order higher. Okay, the Young modulus of the material is 2 order of magnitude higher than the stress required for the fracture to happen. So this is some rough values which we should remember, like by to what extent the fracture strength is lower than the modulus of the material. Okay, so with that we have solved this question number 13. If there is any doubt in this question, please let me know. Okay, there is no doubt. Very good. Let's go to the next question, question number 14. True and false. According to the Griffith, any stress will cause a crack to propagate if given enough time. True or false? Any crack will propagate. Any stress will cause a crack to propagate. Answer is false. We have saw in the class that this is stress applied and this is the crack length. I have to, for let's say my material has the crack length of this particular size. Okay. More is the more I'm going in the y direction, higher is the crack length. For example, I have this crack length. Any stress will cause the crack to propagate. For example, let's say I'm in this particular region. I'm applying this much stress for this particular crack. This is a safe zone. This is unsafe zone. So this much amount of stress is not sufficient for to cause the propagation of the crack. Now let's say I'm increasing the stress. Now it is unsafe. So if I increase if my value is more than the critical value, which we have just now in the last question we found that sigma f, in that case our crack will propagate. So any stress will cause? No. All the stresses which are greater than the critical stress that we have found, fracture stress. Okay. So the answer is false. Let's go to the next question. The B1. The mechanical energy change due to the cracking is proportional to the square of the crack length. Mechanical energy change is proportional to the square of the crack length. What will be the right answer here? Is it true or false? This is something which we have saw in the class, that the change in the mechanical energy for the cracking, it is proportional to the crack length square. Alright. Also, the stress applied divided by the modulus. So we can see that the mechanical energy change due to the cracking is proportional to the square of the crack length. The square of the crack length. It is true. Next part. Higher surface energy material are more resistant to the crack propagation. Let's not talk about any formula right now. We just intuitively will try to answer this. High surface energy material are more resistant to the crack propagation. If the surface energy is higher, what does it mean? I'm trying to propagate this crack, mean that I am trying to put a additional surface area. If the crack is propagating, for example, I'm making the crack over here. Let's say I'm making a crack over here. What I did, I increased two surfaces. One is over here, one is over here. Right? Now, if the surface energy is very high, will the crack will propagate? It means that my specimen doesn't want this. Right? If the surface energy is very high, it means that the process which I am doing, it is going to increase the energy to larger extent. Are more resistant to the crack propagation. Yeah, right now it is not going to do that. So higher surface energy material are more resistant to the crack propagation. Answer is true. Now let's try to answer this by the equation. Sigma f is equal to the, we know, root over 2 gamma e divide by pi times c. Higher the surface energy means higher the gamma. If you are increasing the gamma, what will happen? Your stress required to fracture will also increase because they are proportional. So it means that if you increase the surface energy, the stress required for your material to cause the propagation of the crack will be higher. So it is more resistance for the crack propagation. So if you want to propagate the crack of the same length in the two material where E energy in the one material is gamma in the one material is higher than the gamma in the second material. So it is very difficult for you to propagate the the same crack length in the material 1 compared to the material 2. You will need more stress to fracture in the first material compared to the second material. So that's why it is 2. Now, the D. Griffith's original analysis was for the ductile material. Is it? Did we study the Griffith criteria for the ductile material or for the brittle material? F. It's for the brittle, right? This is false. Very good. So the final answer we can write false, true, true, and again false. Any doubt in this? Let me know. Okay, since there is no doubt, let's go to the next question. Clear? Great. Question number 15. The question says, why did aircraft design switch from the square to the round window? For the better aesthetic, to remove the stress concentration at the corner, to decrease material cost, to improve the visibility. Very good. Option B is the right answer. To reduce the stress concentration, we have saw in the class that the stress concentration for the square, this will be higher. For the, if the corners are very sharp, this will be the smaller will be this value. For the sharper corners, the value of this is smaller, and so this value will be even more higher. Smaller is this, and so the applied, even though you apply small amount of load, the material will feel, that particular section will feel larger load. And for the corners, for the sharp corner, this is a problem. So that's why we removed, and in the aircraft you will see that the round windows are there because this will be higher in that case. For the round windows, this will be higher, and so in that way we can decrease the stress concentration, and the durability of the window will be higher, it will be good, right? So option B here is the right answer. Let's go to the next part, question number 16. Okay, after this I have only one question, so we can finish this question. If the surface crack caused fracture in the brittle material is made twice as deep, the fracture strength will, what will happen? These are the list of the options are given to us. If the surface crack causing the fracture in the brittle material is made twice, so initially it was C, finally we made the crack to be the 2C. So what is going to happen to the fracture strength? First thing is very clear, we increase the crack. We saw in the class that when the professors took two pieces of paper, where in one case the crack length was smaller and in another case the crack length was larger. In the larger one, it required less stress. So it is very evident that the final stress, the fracture, it will be lower than the initial one. So that's why everywhere the decrease is there. Now by what amount? So to answer this, we'll use the Griffith criteria. So from here we can see that the stress required for the fracture is inversely proportional to the root over C, right? So now initial, let's say my initial was the sigma 1 initial, sigma 2 was final. So what I will get, the initial crack length it root of C and final crack length is 2 times of C. I just divide them. So what I will get, sigma 2 will be equal to the sigma 1 divided by root over 2. From here you will get this. So what we saw, it is decreased by the factor of root 2. So option A here is the right answer. Clear? So if you keep on increasing the crack size, now let's say instead of twice, I made it 4 times. Instead of making it twice, I made the crack size to be the 4 times of C. In that case, what I will get, the fracture strength, the sigma required F will be half. Right? Instead of root 2, we'll get the root of 4, which is 2. And so in that case, option B will be the right answer. So very good. With that, we have solved the question number 16. Let's go to the next and the final question, question number 17. Match the pair. Finer the grain size. Remember, whenever we are talking about the ductile brittle transition temperature, more is the ductility, lower will be the ductile brittle transition temperature. More brittle the material is, higher will be the ductile brittle transition temperature. Okay, now let's go to the question. The first one, finer the grain size. Made grain size finer, it is leading to the more ductile specimen, right? So now we can see that the option, it is more is the ductility. It's option B, right? Option B is the right answer. Very good, Omkar. High carbon content. If we are increasing the carbon, what we are doing? Either we are making it more and more brittle, right? For example, cementite. Why we not use the cast iron? Because it has more amount of carbon that it made the cast iron to be the very much more brittle. So we are not using. Higher the carbon, more is the brittleness. Yeah, very good. So option A. Great, guys. FCC structure. BCC is more temperature dependent. The yield point is more temperature dependent compared to the FCC. FCC eliminate the ductile brittle transition temperature. We have saw in the class that in the case of FCC, it is not, and that's the reason why for the ship, so in the Titanic, instead of using the BCC iron, if they would have used the austenitic iron, austenitic steel, the fracture will not have happened. The accident will not have happened. Okay, because in the FCC there is no ductile brittle transition. Like now the last one, fourth one. See, one more thing. High carbon content. High carbon content. We saw in the class. Let's say here the carbon content is very low, 0.8% carbon. The temperature of transition, ductile brittle transition temperature is over here. Now, if I increase the weight percent of the carbon, one more thing will happen. Initially, this thing which was very sharp, the transition will happen very gradually, 1 weight percent. Also, 2 weight percent. So one more thing, for the higher the carbon, if you keep on increasing the carbon percent more, so what will happen? The transition will also be very gradual. So the second one, the second high carbon it has two answers, A and C. Now, notches. If my specimen has notch, either am I going to the more ductile or it's a more brittle. Notches are more, it means that it is more brittle. Okay, and in the case of brittle material, we know that the ductile brittle transition temperature will be higher. Okay, so let's write down the final answer. First, 2, 3, and 4. The first one is going to match with the B. Second one is going to match with the A and C. The third one is with the D, and the fourth one is going to match with the A. Right? Great. Okay, guys, let me know if there is any doubt in whatever we have discussed till now. This was question number 17, 16. Just go through each questions one by one. Here we discuss about the Griffith criteria. Here also, it was more or less related with the Griffith criteria, only that we are getting the highest stress concentration at the corners. Couple of questions on the true and false on the Griffith criteria. Numerical, and this was our observation on the stiffer and the floppy paper. Energy absorbed in the brittle and the ductile fractures. We solved the question on the isostrain. Okay, and these are the true and false based on the isostress and isostrain. Again, this is the isostrain condition. So we are talking about the composite. Then we discussed about the creep phenomena, creep mechanisms. Okay, how the factors are going to change, under what temperature the creep will happen, and which material can undergo the creep depending upon the testing temperature. Okay, Latin solder, which is very famous for the creep materials, creep phenomena to show, and then a true stress and true strain things which we have discussed. So whatever we have discussed till now, please let me know if there is any doubt. Okay, since there is, so can you explain the Titanic failure? Very good. Titanic failure happened. The reason was that the ship which they made, it was made up of the BCC iron, BCC steel. The structure was BCC. So what has happened that this is my yield point and this is my fracture point. Okay, we know that if we go to the low temperature, what is going to happen? A ductile to brittle transition will happen. Right. So the material which was ductile, it will become very brittle. And remember, the ship was running for a very long time, and the water was very cold. Iceberg, it hit the height iceberg, so temperature was very low. So during that time, what the our material, the steel which made up of it became the brittle. The reason is that, see, if we go to the high temperature side, here we can see that the yield point is will happen first, and then the fracture will happen, right? Okay, so but if we go to the lower temperature side, what is happened? The yield point will not reach the fracture. The brittle fracture will initiate first because our material is very brittle at that lower temperature. This is for the case of BCC. While instead of BCC iron, if they would have used the FCC iron, okay, then in that case, this wouldn't have happened. The reason is that they don't cross each other. In the case of FCC iron, this ductile to brittle transition temperature. This don't happen. The reason is that the yield point is not temperature sensitive. So the reason that why it happened, the ship which they made, it has the front part, the one which was collide, it has already transformed. Instead of being the ductile, they assume that it's a ductile. They at that particular time, this particular phenomenon of ductile to the transition, it was not very evolved. They were not aware about that. That if we go to the lower temperature, our ship can become a brittle. And this is what happened. And once it hit the iceberg, it fractured. It shows the Griffith criteria. It's fractured it shows the brittle fracture. Brittle fracture, it means that less energy is absorbed. While if the material would have been ductile, it would have absorbed more energy. If the ductile material would have hit the iceberg, it would have absorbed more energy and it wouldn't have fractured. But in the brittle fracture, it absorbed very less energy and so it fractured. So this is the reason of the Titanic failure, and it is related with the ductile with the transition temperature. Now everyone gives some different reason, like depending upon the field in which they are studying. Okay, so but if we see from the material perspective, this is the case. Very good. Yeah. So I have couple of announcement. With this week 12, like from week 1 to week 12, we have completed the 12 doubt solving sessions. One announcement is that tomorrow, from morning 11 a.m. to 1 p.m., I will take extra doubt solving session. Okay, for 2 hours. So if you have any doubt, like you go through from week 1 to the week 12, if you have any doubt, please feel free to let me know. Okay. Also, if you post it in the group, that Q&A forum, doubt solving forum, then I will note out that question and I will prepare the proper answers for that, so that I can print and I can directly show you what are the things are there. And I will also be prepared more from your question perspective. Anyway, if you have any doubt, please let me know, and you can join tomorrow. The link will be the same, the one which I has provided to you. It will be the same link. So the tomorrow session will be the last session considering this particular course, and I have some question bank with me. If you are appearing for the exam of this particular course, then that question bank will be very helpful to you, and I will provide that tomorrow. And last thing, if any of you are looking for the internship, then you can let me know, and like there is a vacancy in my lab, and where the internship can be carried out, again in the department of the metallurgical and materials engineering. Okay, so with that, these were the list of the announcement which I wanted to make. If you have any doubt, let me know. If not, let's find out today's class. I'll meet you guys tomorrow around 11 a.m. Okay, great.